Good. Ladies and gentlemen, let me first start by thanking the organizers of this meeting. It's been quite an exhausting week. I think with 5.5 days, I think I've probably heard as much about evaporating black holes in the last 5.5 days as I need for the next 40 years. But we've certainly done the subject proud. And of course, we wouldn't be here were it not for Stephen's work 40 years ago. And so I'd like to start. The worst part of every conference, I'm sure you all agree, is the group photo, and you'll remember this being done a couple of days ago. I dug this one out. This is another group photo from 1970, summer of 1970, and here is Stephen in the front row with Martin Rees, and there's a very youthful-looking Paul Davies standing at the back. And so it's a pleasure to be here all these years on, and to be with so many old friends and colleagues, and Stephen in particular. And thank you, Stephen, for summing up so well in the last 10 or 15 minutes what your position is as regards the whole black hole information issue. I want to take a somewhat broader sweep, and what I have prepared here is a mixture of things we've been talking about over the last few days, and one or two things that we have only just touched upon. And so these are really what I would regard as unresolved issues. I think this subject is not closed. There's still plenty of work for young people to do, which is good. And let me begin first with the observational aspects. Now, a lot of people forget that Stephen's first paper on this was called Black Hole Explosions, and there the emphasis was less on things like information, more on whether it might be possible to observe the end state of black holes as an astronomical phenomenon. Now, the point here is that if microscopic black holes were to form in the very early universe, then over the age of the universe, the runaway evaporation process would become quite explosive, and they disappear in a puff of charged particles. And if this takes place in an astronomical background magnetic field, then there will be a pulse of electromagnetic radiation which could be detected, and observations were carried out to see if this phenomenon was taking place. And it would be truly wonderful if such pulses of radiation were detected. Well, that whole subject sort of faded away, partly because I think people exhausted the observational capabilities, although that could be easily resurrected with something like the square kilometer array. But I think also because of a general sense that microscopic black holes were unlikely to exist. These would be primordial black holes made in the very dense phase just after the Big Bang. But current thinking is that they're probably not there. But I wonder if we're being a little too quick in dismissing the possibility of black holes of subatomic dimensions. So maybe there is still room for resurrecting this observational program. I don't want to dwell any more on that, because mostly the people here are theoreticians, and we have had all sorts of discussions, and I'm not going to summarize the back and forth of the last several days about the information paradox, breakdown of unitarity, existence of firewalls, the stress energy momentum tensor, and the back reaction, and a lot of issues that have swirled around depend on the consistency of the semi-classical approximation and where it might break down, whether it breaks down at Planck scales or something above that. These are really unresolved issues. I think I always remember Mike Duff years and years ago drawing caution to the use of the semi-classical approximation, in which we couple the expectation value of T mu nu to a classical geometry, and the circumstances under which that may or may not apply. I think there are many unresolved issues around that. The last one, Stephen Fulling put in at 0.1.5 or 0.5 or something. So he quite rightly says that we really weren't worried about information loss back in the good old days, because there was a singularity inside the black hole, the information could go into it and disappear. And now it's true that quantum gravity may change the singularity, and we don't know into what, but it's entirely likely that it changes it into something with a more complex or complicated topology, and these things come into fashion and go out of fashion, but there have certainly been phases when people have thought of black holes as portals to other asymptotically flat regions of space-time, other universes, if you like, connected by wormholes or bridges or space-time foam, and so all this sort of terminology, a lot of it going back to Wheeler in the 1950s, but we certainly cannot rule out that even if the singularity is removed, that quantum gravity replaces it by more elaborate topology. And under those circumstances, unitarity is meaningful, of course, only on the, if we take a God's eye view on the entire space-time, and not just in our restricted region of space-time. So there seem to me lots of escape clauses that could, in future, be used to get around the information loss problem for those people that have a problem with it. Everyone here is working on the assumption that quantum mechanics has got to be the correct and ultimate theory of the universe as a whole, and it doesn't break down anywhere on any scale of size or complexity or anything else, any other parameter. If you go to the great wide world outside and talk to physicists, very few of them would be prepared to be so bold. I think they would all entertain the possibility that we cannot extrapolate unitary evolution to the universe as a whole. I'm sort of agnostic on that point, but many theoretical physicists would think it's simply going too far. Now, I want to turn now to some of the things that only got touched upon, and in the discussion we just had, the question of trans-Planckian modes was raised. This is Stephen's original construction, where we have to trace the modes from Scry plus back through the collapsing star to Scry minus and perform a Bogolubov transformation between the in states and the out states, and this famously leads to these exponential factors, which is the same as the exponentially escalating redshift. And so what this means is that Hawking radiation with say, everyday photon wavelengths out here would correspond to stupendously high frequencies down here. And the question is, what should we do about this? Should we simply say, well, this is a formal mathematical construction, it doesn't really matter, it's just an intermediate part of a calculation which gives us a result that we believe, and so we'll ignore this. And it has been largely ignored, but Ted Jacobson has recently resurrected it. It was pointed out way back in the mid-70s that this is an issue that perhaps should be addressed. What we would really like is to be able to derive the Hawking radiation by some sort of alternative calculation that doesn't get tangled up with this. The point being, if you put a cutoff in here, say at the Planck length or a trillion Planck lengths, then this whole calculation gets messed up. So that's one issue I don't propose any more about. The question of gravitational entropy, so Faye gave us a lovely talk yesterday in which she introduced this set of ideas, goes all the way back to Tolman, really, in the 1930s, but was particularly championed by Roger Penrose in the late 70s. The issue is very easily explained, that when we look at the history of the universe, the state of the universe just after the Big Bang was one of smoothness and near uniformity, and the ripples in the CMB, remember, only 1 part in 10 to the 5 or so. So that the universe starts out with matter and energy distributed very smoothly, and then over time the material is clumped together, and this type of gravitational aggregation or clumping is what drives most of the irreversible processes we see in daily life, gives us the so-called arrow of time. And the natural end state of that clumping is, of course, a black hole. And so we can think of the black hole as the completion of a process of gravitational aggregation. And it's for the black hole we have a precise formula for the entropy. But many people, and particularly as I mentioned Penrose, feel that somehow one ought to be able to capture the concept of entropy and the inexorable rise of entropy, in this case the inexorable rise of clumpiness, by some sort of measure of the degree of inhomogeneity of the gravitational field. And the square of the Weyl tensor was one idea that was mentioned briefly in passing. This issue is unresolved. One of the big problems about trying to generalize gravitational entropy from the black hole case to this more general gravitational field is that the black hole formula has Planck's constant in it, and this is a collection of stars. There's no obvious connection here with quantum effects. Yesterday, Faye raised the issue about how far the generalized second law can be generalized. So the generalized second law, let me remind you, is where we include the entropy of black hole horizons with the overall thermodynamics of the system, and so that there can be a trade-off, an exchange of energy and entropy between the black hole and its environment. And I think we all believe that if you take the sum of the black holes and the entropy of the environment, that the generalized second law will be respected. That is, that the total entropy is not going to go down. So the question is horizon area always a good measure of entropy? And in particular, when we extend horizons to cosmology, and the classic case is de Sitter space, when we do that, is it always the case that, say, 1 square centimeter of black hole horizon is worth the same as 1 square centimeter of cosmological horizon? And if we wish to make a strong pronouncement that the generalized second law should apply in all cases to all horizons and all matter in the universe, can we use that as a filter to rule out theories where that goes wrong? And again, we had some discussion about that. I want to just pick up a couple of points. So let's take de Sitter space as the case that is much studied. And it is certainly true that a particle detector sitting at the center of coordinates in de Sitter space will click, click, click and register a thermal spectrum with a temperature that depends on the radius of de Sitter space, or the cosmological constant. And there is there are the numbers we want. And that seems like a very close analogy to black hole horizon entropy. And it's been taken as such, I think, by most people since. But when you dig a little bit more deeply into this, there are some differences. It's not so completely clear. The first thing is that the stress tensor that you calculate for the vacuum state that gives rise to the thermal response does not correspond to thermal radiation. When you calculate the stress tensor of the Hawking effect out at infinity, it looks just like a flux of thermal radiation, or in the Hartle-Hawking case, a bath of thermal radiation. You might expect de Sitter space to have a T mu nu corresponding to a bath of thermal radiation. It doesn't. That would be that. That's what you actually get. It just renormalizes the cosmological constant. So T mu nu is not playing the game. A particle detector responds thermally. T mu nu does not correspond to that. Is there an information paradox for de Sitter space? Well, I'm not sure what that even means. You can allow a galaxy to go across the de Sitter horizon. It's gone. It's disappeared from your patch of the universe. How much information is hidden behind it? Well, an infinite amount. So unlike in the case of the black hole, whereas Bekenstein told us many years ago, the implosion of n particles into a black hole means we've lost roughly n bits of information. In the case of de Sitter space, it seems to be infinite. And de Sitter space doesn't evaporate. It doesn't, as it were, give us back entropy in the form of thermal radiation that we might have previously attributed to the horizon. So there are these differences, and the question is, do we have any rights, given the somewhat suspect nature of de Sitter event horizon, do we have any right to suppose that a generalized second law will apply there as well? Well, this is a question that actually, and Larry Ford mentioned this a couple of days ago. This is a question that he and I worked on quite some years ago, because we looked at the case where there's a black hole at the center of the universe, so to speak, and here's the de Sitter horizon. So we have two horizons. This one's hot and that one's cooler. There's a flow of heat from the black hole to the de Sitter horizon, and eventually the black hole evaporates and you're just left with de Sitter space. And if you want to be really clever, you can put a shell of matter around the black hole, a static shell of matter, and that depresses the effective temperature outside of the system, so you can then get a backflow of radiation. The de Sitter horizon can actually be hotter than the black hole horizon. So you can play those sorts of games, and you can ask if there's a trade-off of horizon area, if it's going from here to here or the other way, if the black hole is giving some of its horizon area to de Sitter space or vice versa, will the books always balance? I don't know if Steve Fulling has, if Larry Ford has the same recollection as I do, but I think we were working in Newcastle and we had all the equations up on the board, and it turned out that Don Page was, this is an in-story about Don Page, which you may appreciate. Don Page was coming to give a seminar, and he walked in and said, "What are you doing?" And we explained this, and he took up the chalk and he started writing on the board, and you know, and he wrote more and more, and we sort of sat back, and he covered the entire board with chalk, and then at the bottom, greater than or equal to 0. That's it, proved. It's a typical Don Page story, that one. So that's the paper that came out of it. Anyway, the upshot is that if you try to look at the interplay between black hole horizon and de Sitter horizon, everything comes out in the wash. Some years later, with Tamara Davies, who incidentally was at Nordita when it was in its Copenhagen phase, and Charlie Limeweaver in Canberra, we looked at a gas of black holes in a universe with a cosmological constant, and then just evolved that with the Friedmann equation, so thus allowing the gas of black holes to disappear across the de Sitter horizon and taking their entropy with it. And then the question is, does the de Sitter horizon increase in area enough to pay for the black holes that you've lost touch with? And the answer is yes, it does. So all that seems good. But now, okay, we can believe that it may work with de Sitter horizons because they're sort of more or less static. But what about more general cosmological models where you have an event horizon, but it's time dependent? That would be the situation. For example, if the dark energy were not to be precisely constant. You can still have a horizon, but it becomes a time-dependent horizon. What happens then? That's something I took a look at some years ago. You can define an instantaneous horizon. Incidentally, the question about the teleological nature of horizons came up at this meeting. I think it is really important to remember that a horizon is the boundary of the past of Scribe Plus. And it depends on all the things that are going to happen in the future. A lot of the difficulty, I think, in wrapping our heads around what's going on with black holes and so forth is that somehow whatever is happening when we're talking about a horizon has no local significance, only globally it's defined. And so you might imagine that in the case where the horizon is time dependent, as it would be in this case, that's the horizon radius, and this is the conformal coordinate defined in the familiar way. You could define a horizon like that. You might expect under those circumstances there would be maybe a violation of the generalized second law, but it turns out that there isn't. So long as this energy condition here, rho plus p greater than or equal to 0, is satisfied, then the horizon area is non-decreasing with time. So this is like a cosmological version of the Hawking area theorem. Anybody who wants that, I can give them the reference to that paper. You can solve some models exactly. This is a radiation field model with a lambda term. That's its behavior. And then you can look at a horizon volume with the radiation entropy. And so you've got an entropy to start off with. You've got some just radiation entropy plus a horizon entropy, and then you can evolve it forward. And at the end, all the radiation's gone, and it's just de Sitter space. And again, you can check that the horizon area just keeps going up, and it does. This is even more remarkable because there's no well-defined temperature in the case of time-dependent horizons. For de Sitter space, I've showed you that there is, told you that there is, but in the case of time-dependent horizons, a particle detector would not even have a steady-state response, let alone a thermal spectrum. And yet it seems that the GSL, Generalized Second Law, is doing its best to be satisfied even in these sorts of cases. And so you can ask yourself, well, what sort of violence do you have to do to physics and cosmology in order to get a decrease in the generalized entropy? And you can do that. There are certainly cases where you can do it. One of these has come up already when we have higher order terms in the gravitational Lagrangian, that there can be circumstances there in which you can get a violation of the generalized second law. The case that is perhaps of most contemporary interest is if we have a violation of the energy condition, that is, if the dark energy is increasing with strength over time, rho plus p negative, or the W parameter is less than -1. And under those circumstances, we live in an approximation to de Sitter space, but the de Sitter parameter gets bigger and bigger with time, or smaller and smaller. The thing accelerates faster and faster, and that leads to the famous big rip demise of the universe. And if you take the trouble to calculate the total entropy on the approach to the big rip, which is to say you take any sort of radiation that might be around plus the horizon entropy, then this certainly shrinks down to 0 as you approach the big rip. So you can get violations of the generalized second law, but that leads me to the question, so what? Do we simply say, well, the generalized second law can be generalized beyond what we originally thought, but not to everything? Or should we, as Fay said, cling to it with Eddington's quote and say that if we discover scenarios where the generalized entropy decreases, we should reject those scenarios? And there are really two attitudes you can take about violations of something as fundamental as the second law of thermodynamics. One is to reject any theory that possesses solutions corresponding to a decrease of total entropy. And the other is you just reject those solutions. The problem about just rejecting the solutions is we can always imagine a super civilization that could manipulate space-time geometry and matter, such as to contrive one of the solutions that would violate the generalized second law, and thus, in effect, create a perpetuum mobile. So I don't propose to dwell anymore on the philosophical aspects of that, but if we really are going to take, and as Fay, I think, pointed out so well, Stephen's great contribution has been to draw the connection between thermodynamics, gravitation, quantum field theory. There seems to be something deep still to be explicated about that linkage, that if we're to do that, we're going to regard that as a sort of foundational principle for doing physics and cosmology. And so anything we place at that foundation, we had better take seriously. And so we might well want to eliminate theories, and there are going to be many, many of them. Your favorite theory, or might be string theory, it might be something else, if it's found to be in violation of this generalized second law, then we might want to reject it on those grounds. So that's sort of ending on a dramatic note. I've already mentioned that. The last thing I want to talk about is another trip down memory lane, and some of you know we've had some discussions of this in the last few days. Back in the 1970s, when we were struggling to make sense of calculating the stress energy momentum tensor to put in the semi-classical equations, there was a sort of dispute going on known as the in-in or in-out dispute between two groups of people that I think we all agreed that in the semi-classical approximation we have some sort of geometrical terms on the left and something on the right representing the quantum field. The question is, what is this quantity here in the wedge around the T mu nu? And Bryce DeWitt, who was very influential in getting this whole subject off the ground, drew inspiration from Schwinger's effective action as applied to QED. And when you do that, you're led very naturally from an action principle to consider the quantity in-out, that is, take the T-menu operator and sandwich it between an in state, it doesn't have to be a vacuum state, but it's simplest to think of that, an in vacuum, an out vacuum, and this is a normalization factor. And that quantity, for those people who came under DeWitt's influence, was the thing that tended to be put on the right-hand side of these semi-classical gravitational equations. Is that so? Sure. Here we have Dowker and Critchley, and there it is. Here we have Hartle and Hu. There it is, the in-out quantity. And here, I'm pleased to say, we have Gibbons and Perry. So, again, that's the in-out. And so this was considered, maybe the right thing to do. But a number of others of us insisted that what you should put on the right-hand side is a true expectation value, not the in-out. They're related through the Bogoliubov transformation, this complicated way. The key thing is that all the divergences, which were the main purpose of studying this, to get rid of the infinite terms in the right-hand side quantity, all these divergences are the same in or in-out, and so really the main, it didn't really matter for what we regard as the main job, which was how to get rid of those divergences. And there the matter may have rested, because I think by about 1980, everyone was persuaded that this expectation value was the appropriate quantity. Everything may have been left there were it not for this gentleman here, Yakir Aharonov, one of the founders of modern quantum mechanics, and I've been collaborating with him for about the last 10 years on a sector of quantum mechanics which has always been there, but it's been overlooked in most of the history of the subject. Extraordinary thing. You think all these years on that ordinary basic non-relativistic quantum mechanics can still contain a sector with predictive power that has not been tested until recently, but it does. And this has to do with what are known as weak measurements. I'm not going to go into this in any detail, but I just want to give you a broad brush idea. When we make a measurement in quantum mechanics, a normal strong or projective or von Neumann type of measurement in an idealized system, you couple the quantum system to, say, a von Neumann measuring apparatus, and then, to use the politically unfavorable, incorrect language, you collapse the wave function. It's a strong projective collapse. Now, in a weak measurement, you turn down the interaction between the measured system and the measuring apparatus to an arbitrarily small coupling. Why would you do that? Because then that means that the results of your measurement, the noise smears them all out, and it's no use to you. And it's true that you don't collapse the wave function, but you don't get any information out. However, you can compensate for that by having a very large ensemble of identically prepared systems in identical initial states. And then you can take a statistical average over that large ensemble. That's something you can do. You can do a lab experiment to actually test this. And the statistical average is called the weak value. And there it is. That's Aharonov's weak value. You take the initial state. This is the operator corresponding to the observable of interest. You take the final state, and you divide by that quantity there. It's only in classical mechanics you can't do this, because in classical mechanics, initial state suffices to fix the states for all time. In quantum mechanics, if you have a large ensemble of identically prepared systems, there will always be a sub-ensemble that will satisfy a final boundary condition, as well as an initial boundary condition. You can take that sub-ensemble and consider weak measurements in between the preparation phase and the final phase. And that's what this weak value represents. And of course, that's just what DeWitt was telling us about. And so, so this sort of long-running, not dispute, but long-running confusion as to what to put on the right-hand side of the semi-classical equations, I think is at last resolved, that we now have a physical interpretation of DeWitt's version, and that physical interpretation is that this quantity here is the weak value of the stress energy momentum tensor. It's the value you would get if you make repeated weak measurements in a system where if at the end of as the system, if you have identically prepared systems, if you imagine having an ensemble of them, then if you take a sub-ensemble that satisfies a final boundary condition where that out state is not just the unitary evolution of the in state, if you do that, then that's the value you get. And so the question is that relevant at all to the real universe? And Aronoff has conjectured that the effect of a special natural final boundary condition would seem to us as a new fundamental law of nature. So if we live in a universe where there's not only a natural initial state, maybe the Hartle-Hawking state, but also a natural final state, then there may well be consequences. I'm not going to dwell too much on this. Aronoff calls this like quantum miracle, so we might notice something very strange. And one case has just come up, we've been discussing it. If you were so minded, you could take the initial state of collapsing star to be the Unruh vacuum. You could take the final state to be the Bowler vacuum, and then you would certainly have a divergence. This in-out quantity, this weak measurement, this weak value, would certainly diverge on the horizon. There would be a firewall. So interpreted in that way, you could certainly have firewalls. The question is, what is the final boundary condition on the universe? Can we say anything at all about the final state of the universe? We all have this prejudice that somehow the universe should be born in a simple or natural quantum state, but we're largely agnostic as to what it's going to end up at in the future. But you could take the attitude that we shouldn't be prejudiced, that the universe may be born simple, it may die simple. And if it's the case, as Charlie Misner was saying yesterday, that we're living at an atypical phase between two de Sitter spaces, the inflationary one and the one in the far future of the universe dominated by dark energy. We're just in this transition phase. It may be rather natural to pick a vacuum in the final phase and a vacuum in the initial phase. And because the initial vacuum will not propagate unitarily to form the final vacuum, the weak values that you would get from cosmological measurements would depart from the expectation values, which is the thing that we have known about. And so as it seems fitting at a conference like this, where deliberations have been really rather conservative, I thought I might end on a speculative note. The subject of cosmology is normally regarded as purely observational or theoretical. The question is, could it be experimental? So just for a bit of fun, I thought I would say, well, yes, there's been at least one cosmology experiment. This was by Bruce Partridge back in the 1970s, was to test the Wheeler-Feynman absorber theory of radiation by taking a microwave antenna to the top of a mountain and beaming it out into the universe and then into an absorbing material and comparing the two. And in the Wheeler-Feynman theory, because the existence of retarded radiation depends on a future absorber, a future boundary condition in the universe, it would show up in the power drain of the antenna. Well, needless to say, he didn't find anything, but it's interesting that this was actually a cosmological experiment. So in that spirit, I'd like to finish by proposing this experiment, that we have a natural initial condition for the universe, which would be some de Sitter space, something corresponding to inflation. We pick one at the end of the universe, the dark energy dominated phase, and then the question is, how will we know? Of course, this leaves open, who is the great selector at the end of the universe that does this, but let's leave that aside. How will we know? Well, here's an experiment that may be able to tell you that if you shine a laser beam into the sky, out of the plane of the Milky Way, then a simple calculation shows that most of the photons are going to escape to infinity. They won't be absorbed. And if it's the case that the far future of the universe is a vacuum state of the electromagnetic field, then those photons had better not be emitted in the first place, because otherwise it can't be a vacuum. And so imagine that we have this absorbing material, and there's a gap here, and this is a photodetector, and here we have the decay of a particle, and this is an EPR type setup, and so we can detect a photon here and deduce that there's one going the other way there, and then we rotate the whole thing like that, and what you should find is that if this is pointing up to the sky in the appropriate direction, you don't detect anything here. And so this would be...
The event what?
You would not detect a photon here under those circumstances if it is the case that the far future of the universe is a vacuum state. And so with that somewhat tongue-in-cheek proposal to convey this entire field into the experimental domain, I think I would just like to thank once again the organizers, and it's great to see old friends, and particularly thank Laura for her tireless work in putting this together and in arranging so much food. And I think maybe a week or two of reduced intake is probably called for everybody. And I wasn't terribly clear exactly whether I'm supposed to sort of round it up and say goodbye, go home, drive safely, or are we going to have some Q&A, and in particular is Stephen going to come back and answer some questions. So I'm going to hand over to you, because you're in charge here.